Right, hello everyone, my name is Martin Unterguggenberger and today I'm presenting TME-Box Scalable in-process isolation through Intel TME-MK memory encryption. So let me start with the problem statement and the contribution. So this work focuses on lightweight and efficient isolation for modern cloud settings. And we achieve this by introducing TME-Box, which repurposes the Intel TME-MK memory encryption for in-process isolation, and we can provide fine-grained and scalable isolation on off-the-shelf x86 hardware. And the core idea is to enforce that sandboxes use their designated encryption keys for all memory interactions to isolate memory resources. And we present a performance-optimized prototype showcasing overheads of 5.2% for data isolation and 9.7% for code and data isolation. And as a quick motivation, so as we heard earlier today, cloud computing is highly optimized for performance and efficiency. And one way to achieve this is to replace heavyweight isolation mechanisms, such as process isolation, with in-process sandboxes. However, the exclusion of process isolation introduces security risks, as memory safety errors would allow to leak private data, such as confidential key material or authentication tokens. And a few examples from the past are the Heartbleed or the Cloudbleed vulnerabilities. All right, let's dive into the TME-Box design. So confidential computing brings new hardware features to x86 servers. And the core idea is to repurpose the Intel memory encryption for in-process isolation. And our design goals are: we want scalable isolation and flexible data relocation, as this is important for cloud workloads. We also want a high number of sandboxes, as we want to isolate a high number of cloud workers through encryption keys. And we want hardware-assisted isolation on commodity x86 hardware, which is available. Which brings me to the Intel architectural memory encryption, which is called Total Memory Encryption Multi-Key, or short TME-MK. And it essentially adds an encryption engine located in a memory controller. And it works as follows. So we have a key identifier, or in short key ID, which gets encoded into the upper part of the physical address. This key ID and the physical address get transferred to the encryption engine. Here, the key ID maps to an encryption key and an encryption mode. And currently, TME-MK is specified for up to 32,000 encryption keys. However, it is platform dependent how many are actually implemented. And this allows the page granular encryption of physical memory. So depending on the key ID encoded into the physical address, the page gets encrypted. In addition to that, with the introduction of Intel TDX, Intel's confidential computing platform, additional support for authenticated encryption was added. So this means that we have data encryption with AES XDS and a SHA-free MAC for cryptographic integrity. So when data is stored into memory, we first encrypt the data, and then we calculate a MAC and store both in the DRAM. And when we load data from memory, we recompute this MAC and also decrypt the data. And the recomputed MAC gets compared against the MAC in memory. And if they mismatch, a hardware exception is triggered and detects the violation. So this means TME-MK provides integrity enforcement through a 28-bit MAC. So how can we design a sandbox with this primitive? And as I already said, the core idea is that sandboxes use the designated encryption keys for all memory interactions to isolate the memory resources. And therefore, we need a sandbox-specific key ID that maps to a sandbox-specific encryption key. So in this example, we have 4 physical pages in memory, and we add one mapping for the first sandbox, and we also assign key ID 1 to this mapping. And now we assign the first page to this sandbox, and we also need compiler support to control the base address and the index for the memory operations. And in this way, as we enforce the base address, we also enforce the use of the key ID and thus control the encryption engine. And through the use of page aliasing, where multiple virtual addresses reference the same physical memory, we can share the underlying physical memory. So we add a second mapping, we assign key ID 2 to it, and also assign the next 2 pages to the second sandbox. And we can do this a third time, where we add a third mapping, we assign key ID 3 to it, and finally initialize the last page with the encryption key 3. So we have 3 sandboxes that are mapped to 4 physical pages, and this allows us to get different views on the physical memory. And then the data integrity detects any unauthorized access of any sandbox. So for example, if we take sandbox 1 and sandbox 1 tries to read from memory of sandbox 3, here we will get a MAC mismatch and the violation is detected. Next, one of our design goals was that we want scalable memory isolation, and therefore we need to find a way to get sub-page granular encryption. And we can also get this through page aliasing. So in this example, we have 2 sandboxes that are again mapped to 1 physical page, and it is currently encrypted with encryption key 2. So it is owned by sandbox 2. And through the aliasing approach, we can encrypt parts of the physical page differently. And as TME-MK, the integrity mode of TME-MK is cache line sized. As this is the granularity of the MAC, this is our smallest granularity. So we can assign parts of the page to sandbox 3. And as soon as the memory is initialized with this key ID, in this example with key ID 3, parts of the page get encrypted. And again, we are able to detect unauthorized access through the integrity exception. So when sandbox 2 tries to read the memory from sandbox 3, this is again detected by a MAC mismatch. And finally, we also want flexible memory management for the allocator. And as our design already provides scalable isolation from a single cache line to full pages, this can be used, for instance, to implement allocator caches. So in this example, we have 2 memory pages, page A and B. We have 64 cache lines on each page, and we assign a few cache lines to 2 sandboxes. And our design can also be used to reallocate more memory to both sandboxes, which provides a more efficient way to manage fragmented memory resources. And the design also allows to relocate data in memory. So for instance, we can take these sparsely allocated chunks of memory and relocate them on a new memory page, page C, to store them more efficiently and also interleave them. Which brings me to the implementation and the evaluation. So the TME-Box framework consists of 3 parts: a LLVM compiler extension, a memory allocator, and some kernel support. So for the compiler extension, we need to reserve a CPU register to store the base address of the sandbox. And we propose 2 modes for that. One where we use the general purpose register R15, and one where we use segment-based addressing, where the base address is stored in the GS register. And we need to instrument all memory operations and control flow transfers to apply the sandbox. And for the memory allocator, we need to initialize and manage memory of runtime data, such as the heap. And for kernel support, we need a syscall interface to assign key IDs to pages, which provides our mappings of the individual sandboxes. For the performance evaluation, we implement the prototype and evaluated it with the SPEC CPU 2017 benchmark suite. And we also wanted to identify the individual elements of the performance overhead, so essentially where the overhead comes from. So first, the vast majority of the overhead stems from the compiler instrumentation itself, as we need to control the base and index for all memory operations. We try to optimize this with x86 segment-based addressing, and the second source of overhead from the compiler instrumentation comes from the restriction of the control flow transfers, mainly from the return address protection, as this is done entirely in software. So second, also the memory initialization has some overhead, as we need to set up the MAC values. And also the memory encryption has some overhead, and to get a better understanding of that, we performed a memory latency test with the LM bench suite. Here we can report a maximum overhead of 6.8 nanoseconds when data is served from DRAM. And finally, also the memory aliasing can have some overhead depending on whether two sandboxes share memory on the same physical page. So for the performance overhead, we evaluated the TME-Box in the GS mode, and we report results for data isolation and code and data isolation. And here we have a geomean overhead of 5.2% for data isolation and 9.7% for code and data isolation. And as I already said, this additional overhead from the code instrumentation mainly stems from the return address protection. So here we could lower this overhead by using, for instance, other hardware features such as the Intel CED shadow stack. And for better comparability and also compatibility, we provide performance overhead results of TME-Box in R15 mode. Here we can report a geomean overhead of 13.4% for data isolation and 17.7% for code and data isolation, which means the segment-based addressing really helps with the performance. So in conclusion, today I presented TME-Box, which repurposes Intel TME-MK for in-process isolation. We provide hardware-assisted sandboxing through encryption. TME-Box allows for scalable isolation from individual cache lines to full pages and flexible memory management for the allocator. TME-Box allows to isolate up to 32,000 sandboxes through encryption keys and is available on off-the-shelf x86 machines. So thank you for your attention. If there are any questions, feel free to ask.
Thank you for the great talk. We have time for some questions. Yeah.
Thank you. This is quite interesting. I love this idea of using MKTME. I think one thing, maybe I missed it in the talk, you already have compiler isolation. So you're already using SFI. You're using native client, basically, which is using R15 and the GS register to essentially enforce a sandboxing area. Why do you need MKTME again?
So you think, your question is, what's the advantage over traditional SFI approaches?
Yes.
Yeah, if you think about it, what FSI does is it statically partitions the virtual address space. So I can say, for instance, isolate this 4 gigabytes of memory. And if you think about it, you need to adapt the allocator to actually support that. So you cannot have this at the cache line level. So TME-Box, the design allows to store the data like cache lines interleaved within a single physical page. So you can store the memory more efficiently.
But you also have a memory allocator. Maybe I'm missing something, but you have a special custom memory allocator, right? And that's basically what a lot of the SFI systems do, right? They have their custom memory allocator to make sure that everything is allocated within the sandbox itself. Yeah. And I think you have to do something similar here to have a custom memory allocator that also needs to be instrumented within. So maybe could you explain that again? Where does the efficient memory come from?
Essentially, what the design allows you to do is to take advantage of allocator caches. So with the custom memory allocator, it's more in a sense that the memory allocator needs to initialize the memory. So essentially, it needs to write the memory to set up the MAC for you. But you can use use the allocator as it is. You can store data from 2 different sandboxes on the same page, which is not possible for traditional SFI approaches, as you need to isolate the entire 4 gigabyte range.
Okay, I'll catch you later. Thank you again for the talk. Yeah.
All right, let's thank the speaker again.